Hi everyone, welcome to one more episode of the MRL webinar series today. My name is Mauro Sardella. I'm the director of the Center Research Facilities here at the Materials Research Laboratory, University of Illinois Urbana-Champaign. As far as the facilities updates, all of you know that we have already opened the facilities to train. We are also offering remote training whenever possible, and we're scheduled to reopen on-site training of new users from July the 13th. So we're already scheduling users for that training with the facilities. Of course, we're following guidelines from the University of Illinois, from the state, in terms of social distancing and in terms of wearing masks and so on. You can find details in our website at the facility section of the mrl.illinois.edu. The webinar series today continues with a talk on optical characterization. If you have been following this series, we are scheduled with talks until middle of July. And next week, we have a talk on nanomechanics with AFM, brand new talk by Jessica Spear. Juan Lopez will follow that with a talk on SACs. Rick Hash will follow with XPS analysis on battery materials, very relevant topic. Then we have Hanhui Zhao, FIB, Atom Probe, later by Tim Spila and Batek. And then I will be presenting perhaps the last one in the series about XRD analysis. So the registration to the upcoming webinars are in the website, goillinois.edu/MRL webinars. You can also find links to our previous webinars where you have the videos that have also been posted in our YouTube channel. Go to YouTube, search for MRL Facilities, you'll find our channel where you have all these presentations that have already been posted and presented. And then this one today, you'll be able to find in a couple of days in that channel. For the ones that are new to this interface, we're using the Zoom software. To post your question for the presenter, just click on the chat box in the lower part of the screen if you're using like Windows or PC, and enter the questions. We'll take care of that at the end of the talk. Today we have a unique opportunity to bring someone with extremely enormous expertise in probably all optical characterization that we offer here in the MRL, including the mainstream techniques like FTIR, Raman, Ellipsometry, Photoluminescence, and so on. My particular pleasure today to introduce Dr. Julio Soares. Julio got his bachelor's degree in physics and then master degrees and PhD degrees from the prestigious University of São Paulo in São Paulo, Brazil. It's the largest university in Latin America. He actually held the position of associate research scientist at the University of São Paulo between 2002 and 2004. He also worked after that at the Materials Science Engineering Department here in campus, and he joined the MRL as a research scientist in 2004, and since 2012 he has been senior research scientist here in our facilities. Julio manages all our laser-based optical characterization facilities here for us. His particular research interest is regarding materials characterization in general, especially optical methods, optical spectroscopy, photonic materials, and due to his particular background of his time in Brazil, home country, he actually has expertise in thin film growth and characterization, in particular 3-5 and group 4 semiconductors. Again, Julio, thanks very much for taking the time to prepare this talk and to present to us here. It's a great opportunity for us to learn the ins and outs of all these popular techniques. So with that, Julio, we would like to welcome you, and we will give you the floor now to present your talk. Thank you again.
Hello, everyone. Thank you, Mauro, for the nice introduction and the opportunity to present here. Thank everyone for joining us today. So as Mauro said, I'm Julio Soares, and today I'll give you a brief introduction of optical characterization of materials. My goal today is to present some basic concepts of the most often used methods of optical characterization. We will not have time to do an extensive presentation of the physics behind each of the methods, But feel free to send me an email after the talk if you want to know more about anything you hear today. We will also be answering questions at the end of the webinar, so like Mauro said, please enter any question you have on the chat box. So optical characterization has been very important to humankind. Nature didn't provide us with an acute sense of smell or hearing like it did to dogs and bears to be able to easily find food or detect danger. But it armed us with the power to do spectroscopy. In my talk today, I'll cover some aspects of optical characterization of materials, talking about a few techniques used for that end. For each of these, I'll mention what aspects of the light-matter interaction are mainly involved and how they change the light properties. I'll also cover the instrumentation typically used and give some examples of applications of each technique, while pointing out to some of their strengths and limitations. In addition, I'll also suggest a few techniques that, when used in conjunction to the techniques that I'm presenting, will give a better understanding of the data acquired with each of those techniques. When we use light to characterize materials, we observe how the light properties change when it interacts with the material. These are some of the examples that we can track of those properties. That interaction will cause portion of the photons to transmit, reflect, be absorbed, scattered, and deflected by the matter. When using light as a characterization tool, we target one or more of these processes to detect how the interaction with the material changed the photons that underwent that process, so that we can gain a better understanding about the processes themselves. Some of those changes we can observe with our own unaided eyes, and we can use that to predict several characteristics or properties of the materials we are seeing, which means that when we look at the world around us, we are already performing optical characterization. Light of different wavelengths will interact differently with matter. While the infrared light is ideal to study the atomic and molecular vibrational levels, photons on the UV and visible region of the spectrum are more appropriate to investigate electronic structure properties because the energy of those photons match the energy required for those processes. Using then specialized equipment designed to measure the changes in the light properties, we can often quantify the material properties causing those changes. For example, like illustrated here, for quantifying the drop of intensity of light for each wavelength passing through a solution, we can calculate what the concentration of that solution is, and also to have some insights about the electronic and molecular or atomic structure of that sample. Measuring intensity change of light passing through or reflecting from a material is one of the simplest optical methods to investigate materials. This technique is generally called spectrophotometry. The two most known modalities of spectrophotometry are the UV visible and near infrared spectrophotometry and the FTIR spectrophotometry, so Fourier transform infrared spectrophotometry. For measurements in the UV and visible, the modern spectrophotometers are generally based on a grating spectrometer. Typically, it consists of one or more light sources, a spectrometer, which is represented by this prism on this schematic, that make the light that will interact with the sample monochromatic. And then one or more detectors to extend the range if we need. Besides transmission, various accessories or configurations on the instrument allow for different modalities of measurements, like if your sample looks like a mirror, specular reflectance, diffuse reflectance, it's more like if your sample is more like a paper, diffuse transmission if your sample looks more like a frosted glass system. Some systems have two probing beams that allows for the compensation of slow changes on the light intensity or the detector response during the experiment, and may also include several detectors or sources to extend the available measurement range. Since the UV and visible photons have energies matching those of electronic transitions in the materials, spectrophotometry can be used to determine the electronic band gaps of these materials. So from the transmission or reflection spectrum of the material, we can determine the absorption coefficient. And then using Tox relation, we can calculate its band gap. Here, the band gap of cadmium sulfide was determined for different substrate growth temperatures, giving some insight on the growth process of that material. Another very common use of the spectrophotometry is the determination of solution concentration, like I said before, by measuring the intensity of an absorbance peak for one of its components. So the more concentrated the solution is, the more molecules are available to absorb light. And then Beer's law establishes that absorbance is linearly proportional to concentration and path length of the light through the material that we're measuring. So by measuring that absorbance, we can then determine what is the concentration of that solution. Talking about Beer law, spectrophotometry is often used on food processing quality control, including that of beer. But that's not the reason really that the law got that name. As you know, light behaves as waves and interfere. Interference fringes present in the transmission or reflection spectra of thin films enable us to determine the thickness or the refraction indexes of those films. Here, a sample composed of 2 layers of different thicknesses is analyzed. So you see more high frequency signal here and on top of a low frequency signal, and those are for the 2 thicknesses of films. The periodicity of the fringes is constant with wave number, so plotting your peak index against the wave number, we get a straight line whose slope is proportional to the product between refraction index and thickness. Most likely you have heard about plasmonic structures and the applicability to new optical materials and metamaterials with very unusual properties sometimes and applications. Plasmons actually play a significant role on the transmission and reflection of light, which enables us to study them using spectrophotometry as well. In this example, we wanted to use this plasmonic crystal to fabricate a chemical sensor. As part of this project, we used transmission spectra collected for many angles of incidence to map the crystal's first brilliant zone before and after exposition to our target chemical. With that, we could characterize the response of our sensor to that chemical and then use it to fabricate the device that we wanted. The lines here on this picture indicate calculated plasmonic modes. So you can see a very good agreement between the measurements and the calculations. Recent spectrophotometry has been applied often on the study of nanomaterials as well, like nanoparticles and 2D materials. These exhibit a very strong optical response with a very minute amount of material. And the optical properties of these materials change quickly when we increase the number of monolayers, change the particle sizes, or dope them. So it thus allows us to study them using this their strong optical response. This is a study where optical properties of molybdenum disulfide flakes were studied as a function of the number of layers. The A and B excitons in this figure arise from a direct band gap transitions at the K point due to a spin orbit split valence band and the generate conduction band at that point. The strong dependence of the optical properties of nanomaterials in their composition also allows us to tailor in their properties to produce a material with the optical responses that we desire, like it's illustrated on this theoretical study published on ACS Nano. In the IR range, the photons have energies that match those of the molecular and atomic vibrations. So if we measure the vibration, the interaction of light with the matter using IR light, we can probe the vibration modes of our materials. Not all the vibrations will cause an absorption in the infrared. The ones that cause the infrared, active ones, are those for which there is a change in the dipole momentum associated with that vibration. For those vibrations which do not cause a change on the dipole momentum, we will not see an associated infrared absorption. For those which do, of course, will have a peak on their infrared spectrum. For measuring the interaction of light in the infrared range, one of the most popular techniques is the Fourier transform infrared spectrophotometry. The FTIR spectrometer design is based on a microscopic interferometer with the mirror of one of its arms moving at a fixed frequency. For each given wavelength, depending on the position of the mirror, we will have constructive or destructive interference, causing a rise or a drop in the detector signal. Different wavelengths will interfere differently for given positions of that mirror. So when a broad range of wavelengths passes through the interferometer, the sum of the contributions of all wavelengths will result in a signal with multiple different frequencies, which combined form what we call an interferogram. When we apply a Fourier transform to this interferogram, we recover the frequency domain spectrum. As applications go, like what happens with the UV and the visible frequencies, we can use interference fringes in the FTIR spectra of a thin film to determine its thicknesses. But the most popular application of spectrophotometry is to study or identify chemical structure through the atomic or molecular vibrations in the material. We call that fingerprinting. This is an example where researchers identified the glue holding inlaid stones on an ancient Chinese sword as natural beeswax. And they did that from its infrared signature. They then used X-ray diffraction as a complementary technique to confirm that identification. FTIR is sensitive to very small changes on the chemical composition of materials, allowing, for example, to use it for identifying the source of a sample from small differences in the composition, say the mineral is coming from different origins, for example. In this case, the authors also used near-infrared spectrophotometry as a complementary technique to fully characterize the samples. These differences that we see on the three top samples are mainly due to the presence of a small amount of iron on them. Other common applications of FTIR include detection of contaminants, like in this case, where the contaminants here are caused by the degradation of machine oil due to wear by using a machine. And there are many other applications as well. But both modalities of spectrophotometry share several strengths and limitations. Their main strengths are that they are simple to do and use, and they're fast. As most optical characterization techniques, they are non-destructive and require little and simple sample preparation, but suffer from a limited spatial resolution and often require the use of standards and or complementary techniques for get an unambiguous result. Several optical characterization techniques use the light scattered by a material to characterize it. You can use both elastically scattered or inelastically scattered light. Today I will talk about a method that uses inelastically scattered light scatter. So that is the photons coming out with an energy that is different than the energy incident that they had. In 1928, Sir Raman reported the discovery that the photon energy of some of the light scattered by material was shifted, was inelastically scattered. For his discovery and its theoretical explanation, he was awarded the 1930 Nobel Prize in Physics, and the fact received his name. When light is inelastically scattered by a sample, the difference in energy of the emergency photons relative to the incident photons is absorbed or released by collective vibrations of the atoms or molecular vibrations in the sample. Thus make the sample, the Raman spectroscopy, ideal to probe those vibrational states of the material that we are analyzing. We already know that vibration modes of atoms and molecules depend on the atomic structure of the material, chemical composition, physical state, and temperature. So Raman spectroscopy can be used to investigate all those properties. And each different material will have a characteristic Raman spectrum, just like it happens in IR spectrophotometry. As it happens with IR absorption, not all the vibrations are Raman active. If you write the time dependence of the polarizability with respect to the normal coordinate psi of the vibration, we can see that Raman components will depend on the change of the polarizability tensor. The selection rules for the IR, based on the change of the dipole momentum of the molecule, as we saw before, will differ from that of Raman, which is based on the derivative of the polarizability tensor at the equilibrium state associated with that vibration. So the set of vibrations accessible by each technique is different. Thus, because the physical principle behind the Raman and the IR spectroscopy are different and different selection rules apply to each technique, infrared spectroscopy and Raman are ideal complementary techniques, allowing for a much more complete study of the vibration properties of the materials when they are used in conjunction. Raman can be used to differentiate between different phases of a material with essentially the same chemistry. All of these samples portrayed here are just carbon arranged in different atomic configurations. Each gives a very distinctive Raman spectrum, and that's why Raman spectroscopy is often used to determine the ratio between sp3 and sp2 carbon in diamond-like carbon coatings, or assess the quality of diamonds, or on the characterization of carbon nanotubes and graphene. Raman is frequently used to study defects in a material, like the incorporation of impurities on a crystalline matrix. In this example, we will use it to study carbon incorporation into cubic gallium nitride as a function of incorporated carbon. For low incorporation, the crystallinity of the sample initially improves, and that's because the carbon starts to fill the nitrogen vacancies present in the as-grown material. With increased incorporation of carbon, the crystallinity degrades again, because carbon then starts to incorporate interstitially. Raman is also frequently used to study lattice defects in 2D materials, where the allowed vibration modes will drastically change with the presence of defects. And that's illustrated here on this graphic that compares the pristine graphene, monolayer graphene Raman signal with a defective graphene layer. And then here, several different layer thicknesses as well. The number of layers, as you see here, will also significantly change its Raman spectrum of graphene, and several other 2D materials. So we can use this technique to determine that parameter as well. This work presents a systematic study for different types of defects in graphene, and show how those defects affect the graphene Raman spectrum. In the inset here, we can see different types of defect will present a different evolution of the Raman peaks, in this case, the D over D prime intensity ratio. So as I said, Raman spectroscopy can also be used to characterize carbon nanotubes, making it possible to distinguish between metallic and semiconductor carbon nanotubes, and also can be used to determine their diameter. Strain distribution in a sample will cause Raman peaks to shift, so Raman spectroscopy can also be used to study the strain distribution on a sample. Here is a study of the strain caused on a sheet of graphene by a nanostructure substrate as a function of that nanostructure. On this other example, it's used to map the strain of a crystalline sample caused by a nano indentation as a function of pressure and determine the different phases formed of the crystal formed. Another popular use of Raman spectroscopy is as a contrast method for microscopy, in particular in confocal microscopy, which allows us to map the presence and volumetric distribution of different chemical species in our sample. So Raman spectroscopy is a pretty powerful technique suitable to investigate many aspects of the atomic structure of materials. It requires very little sample preparation. It's complementary to Fourier transform infrared spectroscopy. As that technique is non-destructive, the main drawbacks are the diffraction limited resolution and the weak signal compared to fluorescence. The weak signal of Raman spectroscopy can limit its applicability as a material characterization technique. The easiest way to overcome that, to compensate for that, is to increase the collection time. That can become impractical sometimes, or increase the excitation power, which has its own sort of unintended consequences as well. But thankfully, there is another way to increase the signal without hugely increasing the acquisition time or the total laser power on the sample. The solution is to use plasmons. Because they can be driven at resonance by photons, they can be used to strongly enhance the electric field locally. Raman scattering is proportional to the fourth power of the electric field. So using this strategy, we can greatly enhance our signal. Surface enhanced Raman spectroscopy makes use of surface plasmons to do exactly that. And it's capable of boosting the Raman signal up to 14 orders of magnitude, according to some calculations. Here you can see that enhancement, though not 14 orders of magnitude, it's very clear that there is a huge enhancement when you use a source substrate versus a normal substrate without the surface plasmons. Both spectra here were collected under the same conditions. So that solves the question of the weak signal that we have, but we still remain with the diffraction limit resolution. This is a confocal Raman microscopy image of carbon nanotubes. We should be much thinner than the about 400 nanometers that they appear to have here. And it just happens, though, that the same scheme that we use for the surface enhanced Raman spectroscopy can also be realized by a single sharp metal tip, such as an NAFM tip or an STM tip. So not only you get the electric field enhancement, but now the source of the Raman signal is extremely localized. And that allows for a ladder resolution comparable to those of the AFM. So you can see that there is a drastic difference in the resolution that we get in the end. Raman spectroscopy is not the only spectroscopy that can be used in this way. This technique, commonly called scattering SNOM, or scanning near field optical microscopy, can be applied to other forms of spectroscopy. In this case, the sample is illuminated by a light source, and simultaneously we will approach a metallic tip to the sample inside that illuminated area. The enhanced electric field caused by the tip in the near field will cause a stronger emission by the sample, which can be measured on the far field. This emission will be still much smaller than the scattered light on the far field by the sample. But using phase-sensitive detection, we can separate the near field signal from the far field background. That allows us to collect signals from a sample that come from a tiny volume inside that much larger illuminated region. So just to compare, proportionally, it is like illuminating the State Farm Center, our basketball stadium here in Champaign, while collecting the variation in the reflected light caused by the bouncing basketball inside it. Using this principle, the nano FTIR microscope is capable of obtaining FTIR spectra of single molecules with a spatial resolution of up to 20 nanometers. And like in this example, studying the amide bands of individual tobacco mosaic viruses, ferritin complexes, and insulin fibrils. Another example of SNOW application for characterizing nanomaterials is the study of plasmons on graphene, either generated by the microscope tip itself, as in this work here, where the reflections of those plasmons launched by the tip by the edges of the graphene flakes were measured, or generated by the interaction of an antenna on the sample and the incident light, and then measured by the metallic tip. In those works, the authors were able to detect the focusing of the plasmon by the specially shaped antenna, and the refraction of those plasmons caused by a thicker flake of the graphene on the sample. Nevertheless, nano FTIR is still limited by a relatively slow data acquisition and the tight requirements it has on the sample morphology to be able to be performed. Another optical property of some materials that can be used for materials characterization is luminescence. Now, luminescence is the property of a material that has of emitting light. When this emission is photoinduced, the emission is generally on a longer wavelength than the light exciting it. Luminescence is not only used on materials characterization, but has a broad range of applications, and it received different names according to its lifetime or excitation mechanisms. When luminescence is a result of photoexcitation, it receives the name of photoluminescence. Its basic principle is that the incoming light photons will promote the formation of electron hole pairs, which will thermalize and recombine emitting photons at characteristic wavelengths to those materials. Those wavelengths will correspond to the energy levels and bands inside the material, the electronic structure of the material. In materials characterization, photoluminescence is widely used in the study of nanomaterials. In this example, it is used to assess the number of monolayers of thin flakes of molybdisulfide, as well as to determine their band gaps. Photoluminescence can be used to study defects in these materials as well, being a great complementary technique to Raman spectroscopy. Here is the evolution of the photoluminescence spectrum as a function of electron irradiation intensity for tungsten diselenide monolayer. Here is a work that demonstrating the formation of a van der Waals heterostructure composed of molybdiselenide and tungsten diselenide monolayers using photoluminescence. The photoluminescence spectral line shape depends on the Fermi level energy and band broadening, so that it can be used then to assess carrier concentrations on our sample. Here, the process was just reversed, so they had some known carrier concentration for several samples, and they combined that with photoluminescence to determine the band gap energy of their sample, indium nitride. The solid lines here are theoretical fitting curves based on a model of interband recombination in the generated semiconductors. And with these fits, the authors determined the band gap of indium nitride to be about 700 millielectron volts. The peak position of photoluminescence will depend on the band gap energy, and that for compound semiconductors depend on the alloy composition as given by the Vegard's law. In this paper here, the authors used that and plotted the photoluminescence peak position as a function of alloy composition, so that would allow them to determine what is the composition by just measuring the photoluminescence spectrum. In fact, since the energy of the emitted photons will match those of the electronic transitions on the material, the photoluminescence can pretty much map much of the electronic band structure of the material, as is demonstrated here for a high purity sample of gallium arsenide grown by MOCVD. In this other example, photoluminescence is used on the evaluation of the quality and width of quantum structures, quantum wells in this case, since those parameters are very related to the energy levels available to carriers on those quantum wells. Photoluminescence is basically an ideal method to characterize them. Photoluminescence has so many applications that it can keep a scientist entertained for a lifetime. The main limitations of the photoluminescence technique is the requirement, the requirement of low temperature measurements for many of the materials, and the fact that not all materials luminesce, some luminesce very weakly. Another property of light that can be used as a probe to investigate the interaction between the photons and the atoms is polarization. In a polarized light beam, the electric fields of all the waves oscillate in the same direction. When that direction doesn't change with time, the light is linearly polarized. If we observe the Y and the X components of the electric field, they oscillate in phase. For a difference in phase of 90 degrees between those components, we will have a circularly polarized light, where that direction will describe a circle. And for a phase anywhere in between, the light will be elliptically polarized. Light can change its polarization state when it interacts with materials. That's the principle behind polarizing sunglasses and photographic filters. They work because light changes its polarization state upon the reflection and allows us to eliminate the glare caused by light reflected from the surface of a lake or from a wet road, for example. Since the polarization of light can change with its interaction with matter, we can use this effect to study some of the properties of the materials. A technique that allows us to do just that is ellipsometry. The change in the light polarization state will depend on the optical constants of the material as well as thickness of the layers that form it. So if we determine the polarization change, we can obtain those properties. In ellipsometry, we commonly measure the ratio between the components polarized parallel and perpendicularly to the plane of incidence of a linearly polarized light beam reflected from our sample, and the phase difference between them as well. From these values, which we commonly express as in terms of ellipsometric angles psi and delta, we can determine, for example, the thicknesses of the film and its dielectric function or complex reflection index by fitting the experimental data to a physical model of our sample. One of the simplest examples of the application of ellipsometry as a characterization technique, and one of the most utilized as well, is the thickness of determination of a thin transparent film. In this case, we used it to measure the thickness of a native silicon dioxide on a silicon substrate. From the fit, using tabulated values for optical constants of the silicon dioxide and silicon, we could determine the thickness of the oxide layer to be about 2 nanometers. And then we can, and in this case, we used XPS and X-ray reflectivity to corroborate our results from ellipsometry. So those are two very commonly used complementary techniques to ellipsometry. The range of thicknesses that can be measured by ellipsometry goes from less than a monolayer, basically, to a few microns of thickness, making ellipsometry one of the most powerful techniques in that aspect. Besides thicknesses, ellipsometry can be used to characterize many other properties of the sample, depending on the model that you have, like composition, roughness, band gap energies, or anything that you can determine from the dielectric function of the material. Like the data tabulated here for the case of cadmium zinc sulfide films that had different compositions there. Determining those properties heavily depends on the model used for fitting the data and can be quite complex. This work from MRL group deals with the complexity of determination of surface roughness using ellipsometry. I highly recommend it if you intend to use ellipsometry to determine the roughness of your samples. We can also use ellipsometry to measure, of course, the optical constants of each film analyzed, like they did here for the cadmium zinc sulfide. And here they also verified the optical constants that they obtained by measuring spectrophotometry as a complementary technique to this. So the strengths of ellipsometry reside on the great sensitivity that it has to small changes on the dielectric function of materials. It's an ideal technique for measuring thin films and heterostructures with flat surfaces and optically accessible interfaces, right? Its main limitations are the need of a realistic model for the sample and the fact that it requires relatively flat surfaces and interfaces for accurate measurements. Many times, besides studying the material properties, we need to study them with respect of their localization on the sample, or to differentiate between different parts of our samples. So the most effective way to accomplish that using light is to form images with the photons scattered or emitted by the material being studied, right? So I'll use the rest of the time that I have here to talk briefly about this other aspect of optical characterization, which is called optical microscopy. It started in the late 17th century with instruments that weren't much more than a simple lens. But then the optical microscope has evolved to become one of the most versatile and used tools in many of the areas of science today. Its working principle is very simple. It uses a set of lenses to bend light and deliver a magnified image of an object of interest to our eyes. Most commonly, the object is illuminated either from the top, and we use the light directly reflected by it, or from the bottom when the light transmitted through it is used to form that image. The level of details that we'll be able to see in our magnified image will depend on the microscope lateral resolution. The main factor that limits how fine a structure we can resolve from our sample using light is that light is an electromagnetic wave, and as such, it will diffract. When you focus light as tight as you can, what you get is a diffraction pattern. For the case of a point light source, you get a pattern of concentric circles that we call the Airy pattern in honor of this guy, George Biddle Airy, which was a mathematician and astronomer who explained this pattern theoretically. The diameter of the Airy disks is a function of the wavelength of light. So the pattern that you would see from a white light point source would look like a circular rainbow, because the red light is diffracted more than the blue, and so on. Another factor that affects the width of the Airy pattern is the numerical aperture of our optical system, which is defined by the angle of collection of the light that we're using and the index of refraction of the medium between the object and our optical system. The higher the numerical aperture, the narrower the Airy pattern will be. The lateral resolution is defined by the minimum distance between two sources at which we can still distinguish them as separate sources. And that will obviously depend on the Airy pattern width. The most universally accepted criteria defining the resolution are the Rayleigh and the Abbe criteria. In the optical axis direction, the diffraction pattern is formed more extensively, so it's more extended, and the axial resolution of a microscope is generally worse than its lateral resolution. Also some characteristics of some of the samples are not very easily visible using light directly reflected or transmitted through the sample. So to observe those, there are several different methods that have been devised through the years. Here are some examples of those contrast methods. We're not going to talk about these ones in particular. I can talk more about that later if you want. But also spectroscopic signals can also be used for contrast methods like fluorescence or Raman scattering. Fluorescence, for example, is heavily used in biological studies as it helps to identify specific biological systems and structures when you use dyes that you target to certain structures in the cell. But one intrinsic problem with it is that fluorescence from out of focus parts of the sample contribute to the final image as a diffuse background. In 1957, Marvin Minsky patented the idea of the confocal microscope, where a pinhole is put in front of the detector. The function of the pinhole is to block most of the light coming from the out of focus regions of the sample. And the more we close the pinhole, the more out of focus light we block. And this increases the contrast ratio between the focused and unfocused light, making the images much sharper. Besides this increase in the contrast ratio, the confocal microscope also has a slightly increased lateral resolution. So in the end, the improvement on the quality is quite noticeable. Here we have an example of a fluorescence confocal microscopy used to image fibroblast cells grown on pattern scaffolds done here in MRL. I really love these pictures. Well, adding the pinhole, we get clearer images, and because of the point spread function of the confocal microscope being much more concentrated than the wide field microscope and much more so in the axial direction, its depth of field is much reduced, and that makes the confocal microscope ideal for optical sectioning, where we collect a series of images at different focus positions to map the volume of our sample. This makes the method ideal for optical profilometry too. Here's an example where the confocal method was used to measure the topography of a shallow scratch on a glass surface. This is another beautiful example where we can see the topography of a butterfly wing and the microstructure of it that causes the color of that wing. Here the eye of a bumblebee. The vertical resolution actually that we can achieve with it by confocal microscope used in 3D optical profilometry is much better than that the diffraction limit would allow. If you're curious about this technique, I recommend watching our previous webinar on this series that was devoted especially to optical profilometry. The greatest disadvantage of the confocal microscope is that the fact that the sample needs to be scanned to form an image. So it renders it much slower than the wide field counterpart. So I hope that that gave you a little broad overview of the field of optical characterization. I would like to thank you all for watching and invite you for our next webinar, which will be held next Thursday at noon, when Dr. Jessica Spear will talk about the versatility of nanomechanics with AFM, atomic force microscopy. If you're left with questions about what I discussed after this webinar, please email us and we'll do our best to satisfy your curiosity. Thank you, and I can take some questions now.
Okay, Julio, thank you very much for this thorough review of the field. Going to the first question, in the Beer-Lambert law slide, which I think is slide 19, why is there a shift in the absorbance peak? I think if you could look up back slide 19, I believe.
I'm trying to look for that here. Yeah.
I believe it's talk about the white line there, that there is a slide.
Yeah, the white line is a little bit more shifted to the left. I don't remember quite well why that is, that the gold, I think the gold nanoparticles was just clustering themselves at that point.
Okay.
And that's why it shifts.
Okay, we'll actually have the records of all these questions here, and then basically we can produce like a more detailed answer if needed to the person who put the question.
Yes.
Good. Second question is comparing a thin film optical band gap measurement if you do by spectrophotometry versus if you do by SEM-CL, cathode luminescence. So I also remind you, Julio, that you can comment on that. We have some of our electron microscopists in the audience as well. They can chip in if they want.
Yeah, so both cathodoluminescence and the luminescence, the optical luminescence, they will give you more or less the same results. Cathodoluminescence, of course, you can assess much more energetic transitions in your sample because the electrons are more energetic than the photons that we can use. They should more or less be the same value. The photoluminescence is a more direct measurement of the band gap. So here you have basically to fit this to a curve to obtain your band gap in the end. The photoluminescence is a direct measurement of that. So it's the band gap transition, that energy that the photons will have when they exit the sample there. Sometimes I would use both techniques because that's a more complete study for your sample. Sometimes it's better to use one, sometimes the other for indirect band gaps. Sometimes spectrophotometry gives you a little bit more information. Some of the transitions that you can have there, especially for indirect band gaps, will be non-radiative, so that there will be no luminescence for it, either cathodoluminescence or optical luminescence. But when you can do from both, I would use both techniques.
Okay, I will jump to a question that refers exactly to the slide that you have there.
Oh, okay.
So is there a suitable way to minimize errors when you are using talk plots to determine optical band gap energy?
I think having better data. So optimize the step size of your spectrophotometry measurements, for example, would be and minimize the noise that you may have on your system. So any noise that you have on your transmittance data will cause errors on that plot.
Okay. The other one is about the SERS technique, SERS.
Yeah.
Can that be used for non-metallic samples?
I'm sorry?
The next question is about the SERS technique. Can that be used for non-metallic samples?
Oh, yes. So what is metallic here is the substrate.
Non-metallic, sorry.
Yeah. So what is metallic here is the substrate, not a sample. For metallic samples, not a lot of metals really give you a lot of signal in Raman at all, right? So Raman is already weak for metals, so it's not a very good technique for studying those. But these are for studying non-metal samples on a metallic substrate that is pattern, basically, that gives you plasmons that you can use for the Raman enhancement.
Okay. How about general requirements for sample preparation before you do optical measurements, Julio? Any advice?
Most of them, all you need to do is glue your sample to a holder or hold it somehow. We have some holders that are just vacuum, so you can just hold your sample there without any glue and shine light on them. Some like photoluminescence, if you want to do low temperature photoluminescence, you of course need a cryostat, so they need to be glued to a holder and then put it in the cryostat so that you can vary the temperature.
But the question is more like surface. I mean, do you need to prepare surface to have a smoother surface before you do what measurements are more tolerant to surface roughness or damage or so on?
Okay, so most of the optical measurements are very tolerant for on surface roughness, so you don't need any special preparation there. When you go for ellipsometry, you need to have a basically mirror-like surface on your sample, otherwise you don't get the specular reflection that you need for the technique to work. Then what we call the tip enhanced spectroscopy. Also, you need a very, very flat sample. In the case of our spectrometer here, or our instrument here, you need to have samples that don't have peak to valley depth more than 2 microns to be able to put it in the microscope there, including the tilt of the sample.
Okay. One more. What's the limitation of non-polarized Raman spectra?
There's a lot more that you can do with the polarized Raman. So you can study crystal orientations, for example, with that, and get much more information about the vibration states of your sample. So the limitation is that you cannot have all that if you don't have the polarized Raman capability. I've been arguing for us to have that here, but so far we couldn't get that yet. We'll see it in the future. We can have some polarized Raman capabilities here. So for the nanophoton, right? For the known mapping Raman that we can do with the photoluminescence system, we can do it polarized as well.
Okay. Next question, I think, is about PL. How do you determine the energy, the band gap energy, using PL, take into account Stokes shift?
Yeah, so you need to pretty much calculate all that, right? So you need to know that you will have a Stokes shift there. That will also broaden the PL peak. So going to lower temperatures is one of the things that you minimize that. But yeah, excitonic bonding energies you need to take into account. The Stokes shift that you have on your sample, you need to take into account when you try to fit or to explain your photoluminescence spectrum. Those are very good questions.
Okay. Well, I guess that's all the questions I have here. We're getting a lot of messages thanking you for this excellent presentation, Julio. I second that. Thank you very much. Do you have any final comment?
Thank you. No, thank you very much for sticking with me until the end. And don't miss our next seminar when Jessica will talk to us about the nanomechanics with the AFM.
All right, that's Thursday next week at noontime Central Time here. We have an audience of close to 100, which was above 100, which was very good, from different parts of the world. Thank you all very much. The video of this webinar will be posted in our YouTube channel within a few days. Thank you again. I hope you guys, for the ones in US, have a safe and enjoy your 4th of July holiday. Thanks everyone. Stay safe. Come back next week. We'll be here. Thank you. Take care. Bye-bye.
Thank you, Mauro. Bye-bye.